In the last lecture, we saw that if you started with an aldehyde or a ketone, that you could add one equivalent of an alcohol using acid as a catalyst to form, in this case, add one equivalent of that alcohol to the carbonyl group, so it's a carbonyl addition. This is an equilibrium reaction, and we could form, in this case, this would be a hemi-acetal, because I've just added one equivalent of the alcohol, and then if I wanted to, I could add a second equivalent of that alcohol or another alcohol, and then form, again, because this started with an aldehyde, I could go ahead and form the full-blown acetal. Now, at the end of that lecture, I talked about basically using cyclic alcohols to do protection of a ketone or an aldehyde, and then I showed you the example of a carbohydrate or a sugar, where a lot of times we might have, let's say, an OH group. We might have OH groups on that cyclic ring, and let's just say, for the sake of argument, we have this one, and we want to do reactions on these different OH groups. Well, we might want to protect some of them as, in this case, acetals or ketals, only we're going to use the cis hydroxy groups here, and we might protect them by using something simple like acetone. So if we react this this molecule, this sugar or this carbohydrate, with acetone and acid, we could actually then protect that part of the molecule, because only the OH groups that are cis would react, so that we would actually protect this as a, in this case, a ketal. And I shouldn't have done that. I'm going to erase, change my color back to here, and we'll just go there. So we could protect those two OH groups, and since the other OH groups were not cis to each other, they wouldn't react. So in carbohydrate chemistry, as people are trying to turn sugars, add groups to different OH groups, a lot of times they'll protect the cis OH groups with an acetone, as in this case the ketal. Well, starting with sugars, in this case, this cyclic form of a carbohydrate or of a sugar is actually, in this particular case, this would be an example of a cyclic hemi-acetal. So if you go on and take biochemistry, or maybe in your genetics or your bio classes, you've talked about different carbohydrates or sugars. There's whole classifications of these. There's 3-carbon, 4-carbon, 5-carbon, and a lot of 6-carbon sugars or carbohydrates. There's different names for them, like you have the aldotetroses, aldopentoses, aldohexoses. I'll show you an example of a ketose, which is fructose, the sugar fructose. But you have all of these different sugars that are possible. And in the case of these aldo, the aldo means that there's an aldehyde functional group. The hexose means there's a 6-carbon chain. The pentoses are 5-carbon chains, and there's a whole classification scheme for these. But each of these molecules, there's actually, in the case of the 6 carbons, there's 1, 2, 3, 4 chiral centers in the molecule. That's not necessarily what the D stands for in terms of dextro, but you can learn about what the D actually stands for later on in biochemistry. But in this case, what we actually do is we have an open chain form of the carbohydrate, and then we also have a closed chain form. So this is just the basic classification scheme that either you have seen or you will see. But what happens, for instance, in the case of glucose, is that there's an open chain form, and then what happens is this OH group on carbon 5 will actually come up and add to this aldehyde functional group. They've written it here as a ring, so you can kind of see the OH is just going to come over, react with this carbonyl, and so you can actually close and form a six-membered ring. Remember that the six-membered ring is more stable than the open chain form, or the six-membered ring stabilizes, in this case, this hemi-acetal, so that this is the cyclic form of glucose, which is called a glucopyranose. The alpha and the beta are basically whether this OH group is on the opposite side of the ring of the CH2 or whether it's on the same side. It's alpha and beta terminology. But the idea is that these carbohydrates, these sugars, can exist in a closed chain form or in an open chain form. And there's an equilibrium, but the key thing is this is just nothing more than a cyclic hemi-acetal. And the same thing's true if you take the five-membered ring here. This is the open chain form of fructose. If you take this OH group attached to carbon 5 and you come and you react it with now a ketone, which is the difference of fructose between glucose, then your OH would again attack this carbonyl, and you would close it up to form a five-membered ring, which is called a furanose. And that furan term, remember, we've seen a five-membered ring with an oxygen heterocycle inside of it. This is a pyranose, that's for the pyran. But then you can form a cyclic, in this case, this would be a cyclic hemi-ketal. So the cyclic forms of these sugars are actually nothing more than acetals and ketals, and they turn out to be fairly stable because they are cyclic. So here's just another example of that glucose. A lot of times what I will do when I originally try and write the structure is I will take this O group and I will bring it up here and then sort of form the ring that way. Change this over to an OH group and then number this carbon 1, 2, 3, 4, 5, and then the oxygen is 6, so that when you make your six-membered ring, here was oxygen that was atom 6. Then we had the carbon 5 has the CH2OH, which is actually this part of the molecule. Then it goes 4, 3, 2, and 1. So if you start with this form, you can then transpose that into a six-membered ring. And in organic, I'm not going to ask you to get the stereochemistry right. You can learn more about that in your biochemistry or your other biology class. Now, one of the key things here is that you can see that later on you'll learn the terms of alpha and beta. It turns out that the alpha-beta terminology depends again on the position of this OH group, and this OH group was the one that was formed as the cyclic hemi-acetal formed. And so these are actually two different diastereomers of these sugars, and these two diastereomers actually can have quite different reactivities, but again, that's a topic you'll learn about later on. The surprising thing is, though, that the open chain form of glucose is less than 1%, and the other 99% is actually in its cyclic form. So if you dissolve glucose in water, you're going to have almost all of the molecules in the cyclic hemi-acetal forms. And that'll become important towards the end of the lecture. Well, you then take those rings, and you can then attach, you can bring OH groups together, and then form these cyclic, take the rings and form long chains out of them. For instance, here's cellulose. And cellulose now is actually, because this is now has two R groups attached to the oxygen, this would actually change that hemi-acetal into a full-blown acetal. So you have lots of those cellulose, the starch, other things are made up of these long sugar chains. So the key where it fits into this part of the course is that these cyclic forms of the sugars are nothing more than simply cyclic hemi-acetals, or in the case of fructose, cyclic, it's a cyclic ketal, hemi-ketal. Okay. So let's go on and talk about more reactions of aldehydes and ketones. In this particular case, this is a reaction of an aldehyde that occurs relatively easily, and that is to react an aldehyde with HCN. Now, when you react an aldehyde with HCN, what you end up doing is, if we were to write this mechanism out, I could think of the HCN as having a plus and a minus, so that I would first protonate, my OH group, and then I could have my CN minus, my cyanide ion, come in and attack this carbon, have that pair of electrons go there, so that I can form this molecule. Now, this isn't actually an equilibrium reaction, because this, trying to bring this pair of electrons back down and reform the double bond, there's nothing that'll leave, because I'd have to break a carbon-carbon bond, which isn't going to happen. So this is a 100% reaction. And when you do this reaction, you end up forming what's called a cyanohydrin. Now, cyanohydrins are kind of useful. They can be enzymatically converted back to HCN, which is a little bit of a poison. But the way that cyanohydrins are typically used is to then hydrolyze the C triple bond N, which is called a nitrile group. In not the last lecture, but the one before that, I laid out all of the carboxylic acid derivatives, and I forgot to mention one because it didn't fit the mold. But you have your carboxylic acid derivatives that have different Y groups here. So carboxylic acid chlorides, carboxylic acids, esters, amides. Well, a carboxylic acid derivative that doesn't quite fit this mold is a nitrile, where you've got a C triple bond N in the molecule. And so it turns out that for carboxylic acid derivatives, the reason that they're called carboxylic acid derivatives is when you react them with H plus and water, which is called hydrolysis, you end up forming a carboxylic acid. That is the definition of a carboxylic acid derivative, something that when it undergoes hydrolysis forms a carboxylic acid. And by definition, a nitrile will also undergo hydrolysis to form a carboxylic acid. And we'll get into the mechanism of that a little bit later, not in this lecture, but in later ones. So when you form a cyanohydrin, what we oftentimes do with that is to then hydrolyze the nitrile group to form a carboxylic acid. And in this case, the terminology for sort of numbering carbons that are attached to carbonyl groups is to basically give the first carbon attached to the carbonyl group a Greek letter of alpha, and then you'd have beta and gamma and delta on down the line. But this can also be called an alpha hydroxycarboxylic acid. And this turns out to be a pretty good commercial care product, you'll oftentimes hear, particularly in moisturizers and skin creams, about alpha hydroxy acids. Well, that's exactly what this structure is, and this is a very nice way to produce lots of the hydroxy carboxylic acid using the cyanohydrins. So for the most part, that's a major use of cyanohydrins, is to form these alpha hydroxy carboxylic acids, which, because of the two OH groups, can hydrogen bond to a lot of water, and they make very good moisturizers or additives to moisturizers. Okay, so there's another addition reaction to an aldehyde. So in addition to adding alcohols to form acetals, ketals, adding water to form hydrates, we can also form cyanohydrins and then hydrolyze those. Now, in each of the reactions, to go back here for a moment, when we added alcohol or water to an aldehyde or a ketone, we had to add acid because we were using a neutral nucleophile. Well, we can also do addition reactions with amines, with what's called a primary amine or a secondary amine. And just so you know that terminology, we classify primary, secondary, and tertiary amines based on the number of alkyl groups attached to nitrogen. So when there's just one and you have an NH2 group, it's a primary amine. When you have two alkyl groups and one hydrogen, it's a secondary amine. If I had three alkyl groups, it would be a tertiary amine. So we're going to see that we get two different products when we add a primary amine versus a secondary amine to either an aldehyde or a ketone. But when we do these reactions, and these are going to be addition followed by elimination, which will be a brand new reaction, we don't need acid. As a matter of fact, we know that nitrogen is a stronger nucleophile than oxygen. Why? Because on our periodic table, we go carbon, nitrogen, oxygen, fluorine. Nitrogen is going to be a stronger base and therefore a stronger nucleophile than oxygen, because we have a horizontal relationship on the periodic table. So we don't need acid for this reaction because the nitrogen is a stronger nucleophile. And as a matter of fact, if I added acid to this mixture, what would happen is nitrogen is also a stronger base than oxygen. So the nitrogen would get protonated. I would end up forming this ammonium salt. And now all of a sudden I've taken a good nucleophile and made an electrophile out of it. So we don't add acid to this reaction because we don't need it. So each of these reactions gives a slightly different mechanism, but they both are going to be considered addition and elimination. What we're going to see is that when we add a primary amine to a ketone or aldehyde, we end up replacing the oxygen with the NR group. And this is either called an imine if NH3 is the amine that's used, or it's also more commonly called a Schiff base if we use just a normal primary amine. And when we use a secondary amine, we actually get a different product, which is called an enamine. And I'll come back and talk about the differences between these and relate the enamine to something that we've actually seen earlier. Well, we saw it last semester, at the end of last semester. Okay, so this is addition and elimination. So let's go through a mechanism of this reaction. And we'll skip ahead and then I'll come back to that slide. So if I take an aldehyde and I react it with my primary amine, what's going to happen is that the nitrogen is going to be able to attack the carbonyl, and then I'm going to move that pair of electrons up. So what I'm going to end up forming, and these are all going to be equilibrium steps, I'm going to end up forming an O minus and then have a nitrogen with 2 hydrogens and an R group attached to it. And this is going to form a basically what's called in German, it's called a Zwitterion, meaning that it has both a negative and a positive charge in the same molecule. Now you may say that doesn't look very stable, and you're correct, it's not. So what happens is that the O- deprotonates the N+, so that a proton transfers up to the OH. So what we end up doing is we end up forming the OH, and then we end up having down here the N. We end up with just a single hydrogen on that. So like this. So this compound is called, believe it or not, it's actually called an aminal. Is this one because it came from an aldehyde? And what would it be called if it was a ketone? It would be called a amacetal, I believe. I only know this because of a research project that I was doing with Dr. Miller before she left the university, and we're still working on where we actually made this compound, this aminal, and I didn't even know it had a name until started to look up in the literature for that reaction, but it is called an aminal. So it's it's sort of the aminal is the amine equivalent of a acetal. So we make this molecule, and what will happen in this case is that because this nitrogen has a hydrogen, and the oxygen molecule, it loses the hydrogen, so we can actually form a double bond between the nitrogen and the carbon. So what happens is, and I'm not sure exactly how this mechanism works, but we can think of it this way. This pair of electrons moves here to form the carbon-nitrogen double bond, and then this pair of electrons goes to the oxygen. So in essence, what I do is I lose H2O from this hydrogen and this OH group, and I end up forming then a double bond between the carbon and the nitrogen. And so this is called a Schiff base. Now, it's called a Schiff base when we started with a primary amine and we still have an R group attached to the nitrogen. If I was to do this reaction with ammonia, so if I was to take and add ammonia to that aldehyde, I would actually end up forming a double bond to an NH. Then this is actually what is called an imine. So there's a small technical difference between a Schiff base and an imine. The imine comes using NH3 ammonia as the amine in this case. But either way, this is an addition followed by elimination reaction to form this Schiff base. So it's a little different than what we did to form the acetals and the ketals. And that's because nitrogen is a different element than oxygen is, and so we form this. Now, it turns out that this is still an equilibrium reaction, and we still form actually water over here as the other product. And so the formation of this reaction actually is, you know what, that actually going back here, that's called a hemi-aminal, believe it or not. The aminal would have 2 nitrogens attached. So that's a hemi-aminal, sorry. But to get back here, in order to push this equilibrium to the right, we either have to use an excess of the amine, but most likely what we do is we remove the product as it's formed by some method, and then Le Chatelier's principle will push that equilibrium to the right. There are other factors, which I'll show you in a moment, that can push the equilibrium to the right as well, particularly if I can make this imine very stable, or the shift base very stable, then that'll also shift the equilibrium to the right. But here's the mechanism of forming the imine or the shift base. So it's addition followed by elimination. So going back a slide here, there are a lot of commonly prepared imines or shift bases. And when you use any primary amine, you form an imine that I've redefined here correctly to be the shift base. When it's NH3, then it's the imine. But it turns out that there's some other ones that have been made historically for various reasons, including adding an OH to the nitrogen to then form this molecule, which is called an oxime. This molecule uses the NH2 that's attached to this whole group, and it turns out that when an NH2 is attached to it, this is actually called a hydrazine. If you remember, back in the Wolff-Kishner reduction, we had N2H4, and that was hydrazine. That's the actual hydrazine molecule. This right here is called 2,4-dinitrophenylhydrazine, and what's important is the NH2 actually reacts with the ketone or the aldehyde to then form what's called a hydrazone. And so if you use hydroxylamine, you form an oxime. If you use 2,4-diphenylhydrazine, you form a 2,4-diphenylhydrazone. This one is called the semicarbazide, and it makes the semicarbazone. And I could get into the historical reasons for why these reagents were at one point very important, and they probably still are. But I think I'm going to skip through that for the moment. I'm sure it's in your textbook if you are a go-getter, ambitious student who actually has the book and has opened it. You can go through and see why those are used. But I think I'm going to skip that at the moment and maybe come back to it maybe towards the end of the year. So these are just some historically used amines, primary amines. Okay, so when you react a primary amine with an aldehyde or a ketone, you make the hemiaminal followed by the shift base, right? And those shift bases are actually useful. Maybe if I get a chance, I'll show you how we were using them in our research project. But when you change this reaction from a primary amine to a secondary amine, it alters the mechanism a little bit. So let's take that same generic aldehyde, but now let's react it with a secondary amine. So you're still going to have the same first step of the nitrogen attacking the carbonyl to form this zwitterion. And you're still going to have this proton being deprotonated by the O- to form the neutral compound. And coming back to this step for a minute, sometimes you'll hear people say, well, this proton just simply transfers up to the O-. I doubt that happens intramolecularly in the same molecule. What's more than likely to happen is two of these molecules are going to come together, and the O- part of one molecule is going to deprotonate the N+ part of the other one. So I think that's more realistically what happens. Is it happens between two molecules as opposed to intra within the same molecule. But either way, you get this neutral molecule. So here's the problem with this neutral molecule, and that is I got no hydrogen on the nitrogen to lose to form a carbon-nitrogen double bond. So here's what then happens. What then happens is that there's usually a CH2 group that's attached to, so in other words, this R group is made up of a smaller R group and a CH2. And so it still wants to form a double bond. It still wants to eliminate. But the way it's going to eliminate now is to actually lose a hydrogen from what's called the alpha carbon, because the alpha carbon is the carbon that was next to, and I'm just going to write up here, this is actually the molecule that I'm really kind of starting with. The alpha carbon is the carbon next to the carbonyl. So what will happen is you'll have this pair of electrons go here, and then the OH group leave. So you're going to end up eliminating H2O. This is usually done with heat or for another reason that I still will come back to in a moment. And what you end up doing is forming now a double bond to this carbon, and then you have your N-R groups like this. Now this is called an enamine, is its name. And this enamine is very similar to a molecule that we've seen before. If I was to change this from nitrogen to an OH group, what would we have called this molecule last semester? Well, I'm not going to make you look that up and have that as part of the online quiz, not this time. But remember, this is a molecule that's half alkene, half alcohol, and so this is called an enol. Where did we see enols? We saw them as the result of hydration of alkynes, and then the enol underwent tautomerism to form the ketone, or the aldehyde. Okay, and if you don't remember that, that's chapter 9 from last semester. So this enamine is the analogous molecule. It has an alkene, an amine, so therefore it's called an enamine. And there are uses for enamines. There are potentially uses for enols, but we'll have to wait a couple of weeks until we talk about what are called enolates when I deprotonate this OH group. We'll have to talk about that later on, of what the use of an enamine is. But the key thing here is that the secondary amine gives a different product than the primary amine. So we get an enamine versus a Schiff base. Okay, so both of these are addition eliminations. Now, let me go back to this slide for a minute, because what happens in these reactions is that you get 100% formation, particularly with the 2,4-diphenylhydrazine. If you react that with a ketone, you get 100% formation of the 2,4-dinitrophenylhydrazone. And here's one of the reasons for that. These molecules right here actually form very highly colored precipitates. Usually they're orange, yellow, or red. And so the equilibrium is actually shifted by Le Chatelier's principle because these things precipitate out of solution. So what these are actually used for are qualitative tests to determine if you have an aldehyde or a ketone versus a carboxylic acid, an ester, an amide. In your lab class, you talked about in IR spectroscopy the idea that you can see a carbonyl in the infrared spectrum. It has a peak, distinctive peak at 16 to 1800. Well, in the old days, before we had really NMR spectroscopy, if I wanted to determine whether my molecule was an aldehyde or a ketone, what I would do is I would add 2,4-dinitrophenylhydrazine to it, and if I saw the formation of a highly colored precipitate, that would be a positive test that my molecule was an aldehyde or a ketone. If I didn't see the formation of a precipitate, then it could have been an alkane, an alcohol, an amine. It could have been a carboxylic acid or an acid chloride or an ester or an amide. So if you see a carbonyl in your infrared spectrum and you wanted to confirm that it was either an aldehyde or a ketone, you did this color test where you just simply added the 2,4-dinitrophenylhydrazine and got that colored precipitate. And the same thing would be true for the oxime, although it isn't. It was usually a white solid. And the semicarbazone the same way. It didn't have a lot of color to it. The reason that the 2,4-dinitrophenylhydrazone forms a highly colored precipitate is because you have all this conjugation in your molecule, which makes it absorb visible light and therefore transmit another wavelength of visible light, which gave it a lot of color. Another reason, another way to you can get 100% formation of the Schiff base is if your C double bond N is in conjugation with a lot of, in particular, aromatic rings, because if that's the case, then the conjugation tends to form a very stable molecule, so that you end up with the equilibrium shifting towards the formation of the very stable product. Okay, so we can either form imines, Schiff bases, or enamines by the addition of amines to carbonyls, followed by elimination. Okay, another reaction of an aldehyde or ketone, which is an extremely useful reaction, is what's called the Wittig reaction. Okay, George, and it's George without the E at the end, George Wittig was a German chemist, and in German W is a V, so this isn't the Wittig reaction, it's the Wittig reaction. He came up with a way to take this molecule called an ylide, and I'll talk about how we get this in a moment, and basically couple it together with a ketone or an aldehyde. And the result is that you formed a double bond with this part coming from the ketone or aldehyde and this part coming from the ylide. So we know how to get a ketone or an aldehyde. What's this ylide thing? Well, the first thing we do to form an ylide is we start with an alkyl halide. So these A and B groups originally came from this alkyl halide. So once we make this alkyl halide and we make our ketone, then we would put them together, we would couple them together to form a double bond using the Wittig reaction. And the first thing is to take this is triphenylphosphine that we talked about briefly in the Suzuki, well, actually it was in the Heck coupling. Phosphorus is right below nitrogen on the periodic table, so it's a fairly strong nucleophile. Phosphorus will come in and basically do an SN2 reaction on an alkyl halide so that we form a phosphorus carbon bond. The phosphorus picks up a positive charge. The idea of the bromine is it's the counter ion to the phosphorus. So we haven't done much nitrogen chemistry yet. We will in the next chapter, but we form this phosphonium ion, and then the Br is just simply the counter for that. But I form a phosphorus carbon bond. Well, then what happens is then we take this phosphonium ion and we treat it with N-butyl lithium. So remember that N-butyl lithium is this carbon ion that's then going to come in and it's going to deprotonate that carbon. So I'm going to form a C- and a Br and a phosphorus plus. Now, you can't actually form a carbon-phosphorus bond here because phosphorus is allowed to have an expanded octet, so it can form a fifth bond. But typically, we just leave it as a C- and a P+, and this is what is called our ylid. So in order to make the ylid, we need to start with our A and our B groups attached to an alkyl halide. So once we form the ylid, then we react it with the ketone. I'm just going to show you this mechanism to kind of give you a sense of what happens. This is not a mechanism that I would ask you to reproduce on a test. So I know everybody's fast forwarding out of this because they don't want to see the mechanism, but life's tough. So here's what happens. We can think of moving the electrons in this direction. Take this pair of electrons from this C and bring it over here to bond to form the carbon-carbon bond. Then take this pair of electrons from the oxygen and use it to form an oxygen-phosphorus bond. So we form this four-membered ring, which is called an oxaphosphatane, or it's also called in the older literature a betane. I like the betane term because it's simple. But this is an intermediate compound that then is going to break apart to form our final product. So I don't even know why these arrows are there. They're annoying and they're not necessarily that descriptive. My arrows are better. So once you form this oxaphosphatane or this betane, what then happens is we move the electrons around. We break the carbon phosphorus bond, move this pair of electrons here to form the CC bond, and then take this pair of electrons from the carbon-oxygen bond and give that to the phosphorus. So one of the side products here is we form this, which is triphenylphosphine oxide is what it's called. This C6H5 is the pH, that's the phenyl group. So then we form our carbon-carbon double bond. So in essence, we've coupled the two groups from the ketone or aldehyde, because this could be an R or it could be an H, either one, with the two groups that are from the original alkyl halide that we used to make the ylid. Okay, so it forms a cyclic betaine, and then that betaine breaks apart to form the final product. And this is a really useful reaction, the Wittig, because it allows us to bring two parts of a molecule together to directly form a double bond. So there's different examples. Let's say that I was to take something like cyclohexanone. If I said, take cyclohexanone, and we wanted to basically take cyclohexanone and maybe add, like, I don't know, we could add this. So if I said, how would you go from cyclohexanone to forming this molecule, we'd have to think long and hard about how to do that reaction. It would probably involve a Grignard. So if you thought about that reaction, you'd take maybe this Grignard, and then it would add the Grignard to the carbonyl, which would have an OH group here. And then you could use H3PO4 or sulfuric acid to dehydrate to form the double bond. But in this case, with the Wittig, all I would need to do is to take this ketone and then form this part of the molecule, and then take this alkyl halide. And so then if I treated this alkyl halide with my triphenyl phosphorus followed by my butyl lithium, I would then make that let's see, I'd replace the phosphorus with, so I'd form this, I'd have my phosphorus plus my C minus, that's my ylide. I should probably clean that up a little bit. How about that? So then once I formed that ylide, I would react it with this. I'd react it with my ketone, and so then I should probably change colors here just to make it a little bit clearer. I would then have this part of the molecule couple with the red part over here, and so you can see that this would be the blue part of the molecule coupled with the red part through that double bond. And so I could do this in one step. What you have to realize with organic synthesis is that typically we don't work with really simple molecules. People may have 20 or 30 carbons in the ylide and another 20 or 30 carbons in the ketone portion, and they want to bring those two, large pieces together through a double bond. And so it's a really nice way of forming this double bond. So it's the Wittig reaction is very important. George Wittig, I believe, won the Nobel Prize because he formed a carbon-carbon bond with a double bond at the same time. So it's been a very valuable reaction throughout the years. Okay. I think we just have a few more reactions here to talk about without mechanisms. The next sort of reaction of a ketone, and this is only a reaction that will occur with a ketone, is what's called Baeyer Villiger oxidation. We take our peroxy acid, same peroxy acid that we used to make epoxides earlier. If we react a peroxy acid with a ketone, we actually insert an oxygen between the carbonyl carbon and the alkyl carbon bond, so that we basically form an ester. And it turns out that the rules for selection is that the oxygen atom ends up inserting on the side which has the larger group attached. But Baeyer Villiger oxidation is very important to convert a ketone into an ester, and you might say, well, really, is it that difficult to do? Well, think about this. If I wanted to, let me just make sure that's not on this next slide. So if I really wanted to, let's say I had cyclopentanone and I did Baeyer Villiger oxidation on a cyclopentanone, what I would actually end up doing is forming the six-membered cyclic ester. And cyclic esters are called lactones. How would I even begin to think about forming a cyclic ester if I didn't have the Baeyer Villiger? And you may say, well, couldn't you just do Fischer esterification? And the answer is yes, but we'll talk about that in a few days when we talk about our esters as carboxylic acid derivatives. So the Baeyer Villiger oxidation is very nice because it allows you to form an ester directly from a ketone, but it's really important if you're trying to form lactones because it allows you to have just a cyclohexanone or a cyclopentanone and really form a cyclic ester very easily because it would be very difficult to form that. So that's Baeyer Villiger oxidation. Okay. Now, the last two, let's see, we've got a couple more reactions here. I'm almost out of time, but we'll do the next, you know what? We'll skip these. We'll skip these and I'll pick these up on the next lecture. So I know nobody wants to listen to me for more than 50 minutes, so I think we'll just stop right there. So what have we talked about? We've gone back and looked at the idea that these sugars, carbohydrates, when they exist in their cyclic form, that's nothing more than a cyclic hemi-acetal or a cyclic hemi-ketal. And we can form cyanohydrins. Cyanohydrins are really useful if I hydrolyze the nitrile group to form a alpha hydroxy acid, which are important skincare products. If I react amines, primary or secondary amines, I get addition followed by elimination. If it's primary amine, I just simply replace the carbonyl oxygen with the NR group. If it's a secondary amine, I actually form the double bond to the alpha carbon that's attached to the carbonyl. That's an enamine. Otherwise, I form a Schiff base. And the mechanisms of addition and elimination we've talked about. The Wittig reaction, very good reaction for bringing a ketone and an alkyl halide together after you've converted the alkyl halide to the ylide. Couple those two pieces together through a double bond. A very, very powerful reaction. And then Baeyer Villiger oxidation, where I react a ketone with peroxy acid and convert the ketone into an ester, where the oxygen adds to the larger alkyl group. It inserts an oxygen in between the carbonyl and the larger alkyl group. Okay. So there'll be an online quiz for this, probably just simply matching products and reactions. If you have any questions, either write them in the survey box on Blackboard or bring them to class and we will go over these.